Okay, so for your Unit 11 practice quiz, the very, very first part of your practice quiz asks you to identify the gas property of these four quantities and then asks you to do some converting to the standard unit. So in the case of the first one, I see degrees Celsius, which tells me that we're talking about temperature. And if I look up here in my helpful conversion factors, I see the formula for converting to the standard unit, which is Kelvin. So Kelvin is equal to degrees Celsius plus 273, or Kelvin is equal to is equal to 24.0 degrees Celsius plus 273, or Kelvin equals, what is that, 297? Something like that. And that's what we're looking for the first one there. The second one, milliliters, tells me we're dealing with a volume. And if I look up above, I see 1,000 milliliters is equal to 1 liter. So I'm going to do the conversion of 2,982 milliliters to liters. I want to set this up so milliliters cancels out. So I'm going to get 2.982 liters, in this case of F2. The next one, grams, tells me I'm dealing with amount of substance. So really we're talking about amount of particles of a gas. Some of you might have written moles, which I think kind of covers that as well, maybe. So I'm going to go up here and I'm going to look and see that 1 mole of anything is equal to its mass on the periodic table in grams. So that tells me I'm going to go grab my periodic table and I'm going to need to figure out what the mass of neon is. So in this case, it's 65.7 grams of neon over 1. 1 mole of neon is equal to, 20.18 grams of neon. So I'm going to take 65.7 divided by 20.18, and the calculator gives me something like 3.255698712. We want to assess the appropriate number of significant figures here. And in this case, the answer needs to have 3 sig figs. So I count 1, 2, 3. I see that 5 will round that 5 up. So my appropriate final answer here is going to be 3.26 moles of neon. And then lastly, this is the one that for some people they felt like they were thrown for a loop earlier today. kPa. Of the 4 measurable quantities, I know that we're now dealing with pressure is what we're dealing with. And the way that you could have figured that out if you weren't sure is the other 3 relationships that we haven't talked about all go to ATM. And ATM is the unit of pressure that we've been using in all of our calculations. So this time I'm going to use that relationship where 1 ATM is equal to 101.325 kPa. So I'm going to set this up to cancel out kPa, kilopascals, which is 286 kPa over 1. In 1.00 ATM, there are 101.325 kPa, kilopascal. So I'm going to take the 286 divided by 101.325. And get something like 2.822600543. Again, this answer needs to have 3 significant figures, so I count 1, 2, 3. That 2 does not round the previous 2 up, so my best final answer here is going to be 2.82 ATM of N2. And so that covers the first section. Any questions here? Yes, sir. Okay. All right. In the next one, you are asked to make a claim and then support that claim with some reasoning. And the what we're going to do here is we're going to talk about what this means. So we're asked about a volume of a gas that's increasing. What will happen to the pressure? So the claim that I'm going to make here is that the pressure will decrease. And I'm going to try to show you if I drew a box here. So if I have like four particles in this box, and then I kind of like double the box in size, and the particles spread out, right? That means that they are going to have less opportunity to collide with each other. So here we would say, like, for our evidence, the volume increases. And in this case here, what we could say is that if there's more space, the particles of a gas will collide less with the container walls decreasing the pressure. Okay. So that's kind of what we're going to be looking at for an answer in that ballpark. Hopefully you can identify that this is an inverse relationship. Okay. In the next problem, you have if the temperature of the gas is decreased. So we're looking at temperature here. So if the temperature of the gas decreases, that is, it goes down, which of the following is true about the statement of volume? Okay. What we need to know is that when temperature decreases, the particles move slower, right? So when there's a decrease in temperature, particle movement decreases. Okay. So if there is a particle movement decrease, that means that they're going to move around less, and that means they're going to need less space to do that. So in this case, our best possible answer is going to be this is a direct relationship because as temperature decreases, the volume will also decrease. Again, slower moving particles needs less area to roam around. The next section, you were asked to calculate a variable of a measurable quantity of a gas based on using the ideal gas law. So the first one says, what is the pressure inside of a 4.5 liter container, which is my volume, when the number of moles is 0.106 moles, and the temperature here is 386 Kelvin. So we've gone ahead and identified our variables enough that we are going to go now and just plug them into our formula. Again, we are solving for pressure. We know the volume to be 4.50. The number of moles we know to be 0.106 moles. We know R is 0.0821, and that's ATM, liter, mole, Kelvin. And the temperature that we're working with is 386 Kelvin. We're going to use our calculator to combine things that we can. So 0.106 times 0.0821 times 386. Is it 386? Oh, I lied. It's not 386. It's 338. Ooh, that could have been a wicked problem there. So it's 338 Let's try that again. I thought that looked funky. So we'll do the 0.106 times 0.0821 times 338. That looks better. So our pressure is still what we're solving for. We have 4.50 liters equals, and this time our value is going to be 2.9414 dot 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 dot. Moles cancels out, Kelvin cancels out, and the actual unit here is going to be ATM and liters. We're going to divide both sides by 4.50 liters. And so that'll cancel out liters on both sides. So I'll do that mathematically. And the calculator gives me a pressure of 0.65366619 dot 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 dot. In this problem, we need to have 3 sig figs. So I count 1, 2, 3. I draw a line that's 6 rounds that 3 up. So my best final answer here is going to be a pressure of 0.654, and the unit is ATM. Questions? In the next problem, it's asking for amount of moles, so we're solving for N of H2 that fills a 4.2 liter container with a pressure of 0.992 ATM and a temperature of 358 Kelvin. So once again, we're going to simply plug things into our formula. And in this problem, I do know the pressure this time. Yeesh. Okay. So I have 0.992 ATM. I have a volume of 4.2 liters. The number of moles is what I'm solving for here. The ideal gas law constant is 0.0821. ATM liters per moles per Kelvin. And our temperature is 358 Kelvin. Now, when we combine what we can, we have our 0.992 times 4.2, and we get a value somewhere around 4.1664. Our units there are going to be ATM and liters. And we're going to combine the 0.0821 and the 358. And we're going to get a value of 29.3918. Kelvin cancels out, so we're going to have ATM, liters, moles, and we're going to divide both sides by the 29. Which again, our units are ATM, liters, and moles. And so when we work that out, we will take 4.1664 divided by the 29, 0.39-ish. And your calculator gives you a value of, let's see, it's 0.1417538 dot 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 equals N. This problem has an answer that's required to be in 2 sig figs. So that 1 does not round that 4 up. So the answer is going to be 0.14 moles of H2 equals N. questions about that one? Hopefully that one wasn't too bad. Going to keep rolling here. This one, I'm frozen. Oh, man. Okay, so we'll see what we can do. We'll see if we can unfreeze ourselves. Much better. Good catch. All right, so in this problem, because you are told that this is at STP conditions, we can use the stoichiometry shortcut, so we don't have to do this in multiple steps, although if a person really was feeling that, they could. Okay. I did a little bit of pre-work here to help us get through this one, but we are going to be converting mass of NaHCO3 to moles of NaHCO3 to moles of carbon dioxide CO2 to volume of carbon dioxide CO2. So I'm going to go ahead and grab my given, which is 42.0 grams of NaHCO3, put it over 1, and I'm going to go mass to moles, mole to mole, and then mole to volume. When I go mass to mole, I need to use my molar mass, and in this case, I've already calculated the molar mass of NaHCO3 to be 84.01 grams, so that's going to go on the bottom. And that's equal to 1 mole. Like so. When we do our mole ratio, we are comparing, in this case, the 2 moles of NaHCO3 to 1 mole of carbon dioxide. So I'm going to put 1 mole of CO2 on top and 2 moles of NaHCO3 on the bottom. And because we are at standard temperature and pressure conditions, we can use this relationship right there. So that means that I'm going to have 1 mole of CO2 on the bottom and 22.4 liters of CO2 on the top. 42 times 22.4 divided by 84.01 divided by 2 gives me a final answer of 5.59933. This answer requires us to have 3 sig figs, so 1, 2, 3. That 9 rounds that 9 up, which creates a little bit of an issue. So our final answer is going to be 5.60 liters CO2. All right. We have one more. Take a look-see at here. One more. Take a look-see at here. All right. So now in this problem here, because we have a lot of things going on, I'm going to first identify my variables. This problem asks me to solve for my volume when I know my temperature to be 297 Kelvin. I know the pressure is 0.800 atm. And I know that the number of grams of lithium is 2.75 grams of Li. So because I've been given a mass, I'm going to use that mass to convert mass of lithium to moles of lithium to moles of Cl2. Okay. So we're comparing, in this case, moles of Cl2 with moles of lithium. So my mole ratio is going to be 2 moles of lithium for every 1 mole of Cl2. Now, I'm going to take the 2.75 grams of lithium, put it over 1. And I'm going to go mass to mole and mole to mole. When I go mass to mole, I need to use the molar mass, which I find on the periodic table. The molar mass for lithium is 6.94 grams of lithium in 1 mole of lithium. And now because I'm using my mole ratio, where it's 2 moles of lithium for every 1 mole of Cl2, I'm going to put 2 moles of lithium on the bottom and 1 mole Cl2 on the top. So 2.75 basically divided by 6.94 divided by 2 gives me a value of 0.198126.8 dot 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 dot. So now that's my number of moles, right? So now I know this quantity right here, which means I can go ahead and actually solve for using the ideal gas law. So the pressure that we were given is 0.800 ATM. Solving for a volume. The number of moles we just identified to be 0.198126 dot 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 moles. We know the ideal gas law is 0.0821, and that's going to be, like always, ATM, liters per moles per Kelvin. And then the temperature here is going to be 297 Kelvin. And I'm going to combine what I can. So I'm going to take the 0.198 times 0.0821 times 297. So that's going to leave me with 0.800 ATM times volume, which is what I'm solving for, which will equal something like 4.83106 dot 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 dot. And really, that's going to cancel out moles and Kelvin. So I'll be left with ATM, liters. And so now I'm going to divide both sides by the 0.8. So 4.83 divided by 0.8 gives my volume, my calculator's volume is 6.03883 dot 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 dot. We do need to have 3 sig figs here. So 1, 2, 3. That 8 rounds that 3 up. So my final answer here is going to be a volume of 6.04 liters of Cl2 gas. So that's your practice quiz. We'll have a real quiz tomorrow, which will follow this same format, although different problems actually, not different style. If you have any questions, please make sure you let me know. Otherwise, good luck studying.